Welcome to Random Maths. In this third video in the Finite Series playlist, we'll be discussing telescoping series. So let's get started. So what is a telescoping series? So the general definition of a telescoping series is as follows. So take a sequence, or take two sequences, AR from R is equal to 1 to N, and BR from R is equal to 1 to N. Then for AR equal to BR plus K minus BR for some positive integer K, we say that the sum from R is equal to 1 to N of A underscore R, which is equal to the sum from R is equal to 1 to N of BR plus K minus BR, is a telescoping series. So that's a general definition. So you take two sequences, and the first sequence is defined as, so the rth term in the first sequence, and then we'll look at the second sequence. So the rth term of any term in the first sequence is given by taking the rth plus k term in the other sequence minusing the rth term in the other sequence. So we're defining one sequence as two terms in another sequence being taken away from each other, and obviously that leads us back to the definition of what a sequence is, a finite sequence is, which I did in the first video. And you can define one sum by the addition. You can define one function by the addition and subtraction of other functions, and this is just a function. A underscore R and B underscore R plus K minus B underscore R are just functions. So you can also think of this as, I'll just quickly do it up here. So if I put this as a blue box, I've not used that yet. You can kind of also think of this as, so if you look at the first video for a lot of more intuition regarding this, but you can think of this as f of r is equal to g of r plus k minus g of r, where g represents the function behind the b underscore r sequence, and so fr is equal to ar underscore r, and g of r is equal to b underscore of r, and that's valid for all r in n. So yeah, it's kind of just taken from that. So watch the first video if you want more intuition of what a finite sequence is. I define a finite sequence before I define a finite series, so please go and watch that. So yeah, so essentially any sequence that's set up as being the difference between the r plus k term in one sequence minus the rth term in the other sequence, and if you sum all them from 1 to n, then that's a telescoping series. So that's a general definition. So now let's move on and give you a quick example of a telescoping series. And just, yeah, before we give an example of a telescoping series, let's just have a look in the case where, because we said for k as a natural number. So let's look at the case where k is equal to 1. We're not going to specify any kind of sequence or series yet for the a underscore r terms or the b underscore r terms. We're just going to keep it general. A underscore r is just a underscore r, b underscore r is just b underscore r, but we're going to look at the terms when k is equal to 1. So let me explain. So for k equals 1, what do we have? Well, we got the sum from r is equal to 1 to n of br, rather than r plus k, it's br plus 1 minus br. Okay, so what does this equal? Well, this equals b times 1 plus 1, so b2 minus b1 plus b3 minus b2 plus b4 minus b3, and so forth. and then we'll do the m minus. Go to m minus 1 here. So b n minus 1 plus 1 is bn minus bn minus 1 plus bn plus 1 minus bn. So this is when r is equal to 1, 2, 3, all the middle stuff. This is when it's equal to n minus 1, that's when it's equal to n. So they're the n terms we're summing up. Now if you notice, some of these terms are going to cancel. So b2 will cancel with minus b2, b3 will cancel with minus b3, b4 will cancel with minus b4, which will be here somewhere. bn will cancel with minus bn. This b minus bn minus 1 minus bn minus 1 will cancel with 1 before. So all we're going to be left with is bn plus 1 minus b1. So bn plus 1 minus b1. Now with a telescoping series there's no nice formula for one, but what we can do is we can simplify the number of terms in the series. So we've got a long series with n terms, and now we've simplified that down to 2 terms. So there's 2 terms here. So as you can see, there's 2 terms here, whereas before there was n terms. So it's worthwhile knowing telescoping series because it makes computing some complex series really easy. This is just one example. So that's when k equals 1, that will be the value of the telescoping series when k is equal to 1. And you can kind of see why, because this is also, remember, this is also equal to the sum from r is equal to 1 to n of b r plus 1 minus the sum from r is equal to 1 to n of br. That's from the addition rule of finite series. We went through that on in the first video. So we can kind of now from that see why the above holds. So if we look at the case when r is equal to, because minus b1 will be given here, so minus b1, and we do blue, minus b1 is going to be given in that equation, but there's going to be no b1 in this equation. Doesn't exist. Trying to cross it out. Yeah, there's going to be no minus b1 in this equation because it starts, because it's b2 plus b3 plus, and this one is going to be minus b1 minus b2 minus b3 plus bn plus 1. This one's minus b1 minus b3 all the way to minus bn. So you can kind of see from this, if you will, I'll make it a bit bigger underneath. You can kind of see why that holds, because let's just do it underneath. Let's just do it. So what we've got is we've got b1 plus 1, b2 plus b. I don't know why I didn't do this in the first place. Apologies. Plus bn plus 1. And what we're going to do is we're going to take away b1 plus b2 plus bn. So essentially, b1 is not going to be deducted, but b2 to bn will be deducted. So another way of writing this, we could write it as follows. So we got this is how we can write it. We can factor some terms out here, right? We can do b2 plus b3 plus bn here. Plus b3 plus, so we can say, how can we, yeah, so minus b1 minus b2 plus b3 plus bn minus, yep, so minus b1, all that, plus b2 plus b3 plus bn plus bn plus 1. So you can see all these terms in the middle are going to cancel, leaving us just bn plus 1 minus b1. The reason they all cancel is because these don't cancel, because these are the only terms that don't appear all these other terms appear in both the sums. So these two terms here, so this term appears and this term both appear in both of these sums, because this is kind of the same term, isn't it? So these appear in both of these sums, but these ones do not. The other two do not. So this term minus b1 doesn't appear in that sum. Well, appears in one sum and not the other, so it appears just in this one, and bn plus 1 appears just in this one. So that's kind of why it's kind of a bit more, if you break it down a bit further, that's kind of the logic behind it. So anyway, let's go when k is equal to 2. And we'll get the same thing. We won't write them out and do the cancelling out naively like we did up here. So like we did up here. We won't do that again. We're going to go straight for the nicer method, which is that one. So let's do k equals 2 now. So we've got the sum from r is equal to 1 to n of b underscore r plus 2 this time. B r plus k, isn't it here? Minus the sum from r is equal to 1 to n of br. Okay, so that's going to be equal to, let's have a look, what's it going to be equal to? b3 plus b4 plus bn plus bn plus 1 plus bn plus 2 minus b1 plus b2 plus bn, and again what we're going to have is minus b1 minus b2 minus b3 plus b4 plus bn. Then we're going to add b3 plus b4 plus bn plus bn plus 1 plus bn plus 2. So again, this term here cancels with this term here, leaving us with just bn plus 1 plus bn plus 2 minus b1 plus b2. So another way to look at this will be as follows. So let's have a look when k equals k, because why not, right? So when k is equal to k, what we're going to have is a situation where we've got, this is the general case for just any k now, b r plus k minus the sum from r is equal to 1 to n of br. Well, we're just going to have, again, we're going to start, so br plus, so bk plus 1 plus bk plus 2 plus bk plus 3 plus all the way to, and then we're going to have k plus n at the end. And we're going to minus, take away b1 plus b2 plus bn again. So like before, what we're going to have is some terms, so k plus 1, some terms are not going to be included. So what we're going to have is the following. We're going to have this going to be equal to, depending on what k is, obviously, but minus b1, minus b2, all the way until, so minus bk, minus dot 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 minus bk, as such. And then we're gonna have plus, so let's have a look. Yep, and we're gonna have minus bk plus 1 plus bk plus 2 plus bn, right? and then we're going to so that will be that, and then we're gonna, so it's like this, and we're gonna have plus, and then we're gonna bk plus 1 plus bk plus 2 plus bn, and we're gonna have all the terms after that now, so plus bn plus 1 plus bn plus 2 plus bn plus k. Okay, so that's kind of what we're going to have again, and we're going to have this will cancel with that, that will cancel with that, and we'll be left with the same thing. We'll have bn plus 1 plus bn plus 2 plus all the way to bn plus k, and then we'll minus b1 plus b2 all the way to bk is basically what we'll have. That'll be the pattern continuing on, because you've got, if you look here, when k is 2 they go to n plus 2, so when k is k we go to n plus k, and k is 2 so we just do 1, 2, k is k so we just go to k. So in other words, we can rewrite the general formula as the sum from r is equal to 1 to k, no sorry, to n, depending on what n is again. So from r is equal to 1 to oh no, sorry, no, sorry, from r is equal to 1 to k, get it right, of b r plus k, so no, bn plus k, bn plus r, yeah, that's it, bn plus r. So we've got bn plus 1, bn plus 2, all the way to bn plus k, yep, and then we do minus the sum from r is equal to 1 to k of b underscore r. So that's kind of what we're going to be doing. So yeah, so that's the generalized formula for them. So essentially the telescoping series, we've defined a telescoping series above, which was like so. That is a telescoping series. And now we're going to say, so we're going to say that the sum from r is equal to 1 to n of b r plus k minus br, that's going to be equal to the sum from r is equal to 1 to k of bn plus r minus the sum from r is equal to 1 to k of b r. So whatever k is, so k is going to be a set term, k might be 20, whatever, we're going to be summing 2k, so whatever k is, 2k rather than n. So this here is summing n terms. This here is summing 2. Well, it depends. We can have 2k terms as well, because we can also write it like this. So it depends how we write it, how many terms we're summing. So instead of that, we can just instead sum, because that's going to be 1. So that's n terms, and this is summing k terms, which is less than n. So telescoping series, we haven't got a nice formula for the series as we did with an arithmetic series, but we've got a way to reduce the number of terms that we're summing. We don't need to sum up n terms, we only have to sum up k terms. So if we've got r plus, whatever, r plus 3 minus r squared, all we need to sum up is 3 terms. Well, it's kind of a cheat, because this is really, you're summing 2 terms up here really, because you're going to have to, because we're treating 2 so 2 plus 3 we're treating, for example, as this is well. Let me do an example. So let's just do bn plus r. So bn plus 1 minus b1. That is not really one term. That's two terms. And then we can say plus, but we're kind of doing 4 operations, not 2. So think of it. We can think of it really as 2n and 2k. So that's why I put it in brackets, because it's not really k terms, it's not really n terms, it's more like 2n terms, 2k terms. But anyway, the point is, I'm going off on a tangent, it's more efficient, so that's great. So now let's look at an example of a telescoping series, an actual example. So the example we're going to look at is going to be as follows. So we'll show this example. Let's look at the case where k is 1, and let's have BR equal to r cubed. Okay, so that means AR, because we're telescoping series, has to be equal to BR plus K minus BR, which is equal to BR plus 1 minus BR, which is equal to R plus 1 cubed minus R cubed. So we're going to be summing this up. So the sum from R is equal to 1 to n terms. We don't know what n is. We can find out what n is, but I wanted to get it in the formula in terms of n as first, then we can choose n whatever we want. So we're summing n terms up, and we're going to be doing r plus 1 cubed minus r cubed. Telescoping series. We know the solution. We've done it above, so let's have a look at the solution above. So the solution is here, just here. We can see it just above. Generalized solution. Let's have a look. So we're going to use this format here. So I'm going to do blue, the middle bit. It's more intuitive than combining them. So let's have a look. So going to k is 1, so we just got the sum from r, because it is two anyway, 2 sums. So that's why I just of bn plus r. So we don't know what n is, but we know what r is. It's just going to be 1. But so bn plus r minus the sum from r is equal to 1 to 1 of br. Well, that's just going to equal br plus 1. There's only one term in the sum. Minus br. So what is that? That's going to be just br. b1, sorry. So we know what b1 is. It's equal to 1 cubed. Because we know how to work out both of these. Both of these can be worked out using just substituting, substituting r plus 1 in, and then taking r, substituting 1 in. So we've got r plus 1 cubed. Yeah. Wait. It's n plus 1, isn't it? It's not r plus 1. Yeah, sorry. It's bn plus 1 we're summing. So it's bn. I was going to say, I was wondering why I had r then in my equations. Minus b1. So yeah, so what I'm going to be doing is I'm going to put n in, not r, for r. So we've got bn plus 1, so we've got n plus 1 cubed, and then we've got minus 1. Now if we know how to expand these quickly, in the binomial theorem, so you can actually expand them by multiplying them out, but I know a quick method to solve this. I'll go over it in another video on the binomial theorem. I'll do a video on that later on. But this here is going to be equal to n cubed plus 3n squared plus 3n plus 1, and then obviously minus the 1. So we just got n cubed plus 3n squared plus 3n is the solution to that. And we're going to look at the binomial theorem in the other solution. If you're not sure how I got from this to this, for the purpose of this video, just literally do the multiplication manually. So n squared plus n plus 1, and then multiply that by n plus 1. I'm not going to continue you can do it yourself. You'll verify, you'll get n cubed plus 3n squared plus 3n plus 1. Okay, so that's a telescope in series, and that's a solution. So we've got the solution in terms of n, which is great. So if we wanted to do the sum from r is equal to 1 to n of r plus 1 cubed minus r cubed, and we're going to say n, so for the case where n is equal to 50, we can now do it. It's going to be equal to, rather than summing 50 terms up and take some time, we can just do 50 cubed plus 3 times by 50 squared plus 3 times by 50. Now I haven't got a calculator on me, but I do because I'm on Windows. Bear with me a second. Calculator. So we can actually find out what that equals. Unfortunately, I'm in tablet mode because I'm typing, so we need 50 cubed plus 3 times 50 squared plus 3 times 50. So 50 cubed, so 50, where's the cube button on here? I've not used this one before. Cubed plus 53 times by 50 squared. No. Go back. Sorry, 50 cubed. I'll do it one more. Try and do it one more time. If not, we will have to. You can do it. Check it yourself on a calculator. Plus 3 times 50 squared. 50. I'm guessing. I don't think I wanted the square root of 50. So, okay, I'm not going to do this. I'm not used this calculator before. I'm sure it's a standard one that you write on. But do that sum on a calculator. You'll get a value, and that'll be the value. And it's quite easy to do. Just plug a number in the calculator, it gets you the value, nice and easy. So yeah, whatever that comes to when you put it in a calculator, that'll be the solution. The reason this is useful is because essentially now we can look at the case when to solve this. So yeah, so the point is we can now use this as an application of the telescoping series below. So we're going to put application. So this will be the last thing I do on this video because it's kind of gone on quite long now. So we already know that the sum from r is equal to 1 to n of r plus 1 cubed minus r cubed is equal to n cubed, so what was it? N cubed plus 3n squared plus 3n. We can factor out an n as well and simplify a bit further. We're not going to it for now. So we know that's the case. We know it's the case. But we also know that from the previous video, the arithmetic progression, we know this. We know that that is equal to n times n plus 1 over 2. You can check out the last video on arithmetic series to find that out. So what if I said, well, rather than just summing the same number, what happens if we sum the same number but the square of each number? So what happens if we do this? What's the solution to that? You'll be like, oh, I don't know. We can use telescoping series, this result here. So telescoping series, which is this result, and we can also use the addition and scalar multiplication rule for finite series to solve the sum of squares. So we also have the addition and multiplication and scalar multiplication rule for finite series. So let's use that now. So if we expand this out, we've got, that's one way of doing it, using the telescoping series, but we can also do r cubed plus 3r squared plus 3r plus 1 plus plus 1, so yeah, plus 1, and then minus r cubed, yeah. Minus r cubed disappears, so we don't have to worry about summing cubes to find out summing squared, which will be counterintuitive. then we get the following: r is equal to 1 to n of 3r squared plus 3r plus 1. Then we can use the addition rule for summing finite series up. So we've got 3r squared plus the sum from r is equal to 1 to n of 3r plus the sum from r is equal to 1 to n of 1. This is obviously just 1 plus 1 plus 1. This is just 1 plus 1 plus 1 plus 1 n times. So just equal to n. This here so we can also use a scalar multiplication rule to do this as well. Plus n, because we've already established that this here is equal to n. We also know that this here, well, we use red. No, we use green. We also know that this here is equal to this here from the previous video, an arithmetic series. Go and have a look. So what we have now is we've got 3 times by the sum from r is equal to 1 to n of r squared plus 3 times by n plus 1 over 2 plus, well, we use 2n over n. We're just getting n. This is still n. Sorry, over 2. This is just me rewriting it as over 2 so I can add the fractions up. So now what we've got is we've got an equation involving what we want to find out, which is this here. So we want to find out this is what we want to find out. We've got an equation involving it just from doing the addition and scalar multiplication of a finite series. And we know that this sum that we use as an example is equal to that, but we also know that this sum is equal to this. So we've got this and we've got this. So we can equate these now. So we can equate both of them because they're equal to each other. So let's basically let's just use I'll kind of use all the colours already, but I'll use green. Screw it. So we know that this is equal to this. Now this was from telescoping series, the content of this video, and this was just from the addition and scalar multiplication rule of finite series. But they're equal to each other, and everything's known except from r squared, so we can just solve it now for r squared. So we'll do it quickly, and that'll be the end of the video. So we've got 3 times by the sum from r is equal to 1 to n of r squared. We combine both of these fractions now, and we combine the top here, so we've got 3n squared plus 3n plus 2n, so plus 5n over 2 is equal to, so what we've got again, we've got n cubed plus 3n squared plus 3n. N cubed plus 3n squared plus 3n. Okay, times by 2 on both sides, so we'll times by 2 on this side, times by 2 on this side, because we don't want the fraction, get rid of the fraction. We'll have 6 times by the sum from r is equal to 1 to n of r squared plus 3n squared plus 5n is equal to 2n cubed plus 6n squared plus 6n. And then we rearrange, so we'll have 6 times by the sum from r is equal to 1 to n of r squared is equal to 2n cubed minus 3n plus 3n squared plus n. Now we'll start factoring the n's out, because might as well now. N times by 2n squared plus 3n plus 1. This here is a quadratic equation. I haven't done a video on quadratic equations yet, but they're really straightforward to work out. In this case, we just need to we can rewrite this in this form. I'll go into more detail when I finally do a video. And then we can say, well, this is equal to 2n times by n plus 1 plus, sorry, made a mistake there, plus n plus 1. So then plus n plus 1, factor out n plus 1, n plus 1 times by 2n, and just times by 1. So we've factored that now, so that's going to be equal to n times n plus 1 times 2n plus 1. And we want the sum from R, we want just R squared on its own, so we drop this 6 underneath, and that's the solution of the equation. So that's the solution of the sum of the first n squared numbers. And we can also use telescoping series and the addition and scalar multiplication rule of finite series to come up with the sum of the first n cubed numbers, n quartic numbers, you know, and so forth, power 4, power 5, power 6, by just taking, so each time, if you want the, for example, if you want the sum from r is equal to 1 to n of r cubed, follow the same methodology as we've done here, but use b underscore r is equal to, rather than r cubed, use r to the 4. And you'll be able to manipulate it, follow the same proof above that I've just did for the r squared, but for the r to the 4. Obviously you're going to get r to the 4 cancelling out, and you're going to have an equation in terms of r cubed by doing the addition and scalar multiplication rule for finite series. Then you're going to also be able to use telescoping series on this as well to get another equation, set them equal to each other again, follow it through like I've done above, and you'll be able to do that. And if you want, you can also do the sum, the first n to the r4, and you can just use b underscore r is equal to r to the 5, and so forth. And you can even generalize it to just say r to the k, and there's a general formula for it as well. You can find it on Google. I don't know it to hand, I'll have to have a look. I'm not going to do it in the middle of a video, but you can generalize it. In order to do that, there's some more kind of stuff we need to look into, so like because we need to know the binomial coefficients, things like that. So I'm not going to go into it all today, but you can, if you want as well, calculate them all by iterating as I've done here. You still would need to iterate, but yeah, you can just iterate using telescoping series and addition rule and scalar multiplication with finite series to find any of them. I mean, one more time as well, if you wanted that, follow it through with this. But you're going to need to go through them in order, because up here we knew, so when we had this part here, we already knew the solution, well, which is that whole thing. We already knew the solution for the sum of this here from the last video. Now, if you're doing the r cubes, you're going to know the solution to the r squareds because we've done it. But if you skip to r to the 4, you would need to know the solution to r cubed. So you've got to do it in order. It's an iterative process that needs to be done in order. But you can do it. So have a go and see if you can do it. I'll stop the video here because I think it's gone on far too long. And I hope you enjoyed this video on telescoping series. Please as well feel free to tell me the answer to that one here by just plugging it into a calculator. And yeah, I'll see you in the next video, and any comments that you feel are relevant to this video, just leave them in the comments below. Any improvements that you think I can make on teaching, leave them in the comments below, and I'll try and help. And also I'll take your feedback on board. Thank you for watching, and see you in the next video.